for shocks to occur. Once the discharge occurred, the force disappeared. So the shock was some form of discharge which reversed the imbalance created by the friction. Throughout history, we were also fascinated with lightning bolts, nature's most passionate displays of power and aggression. Most cultures assumed this was a divine force, outside the reach of human hands, and was therefore reserved for the gods. Up until the 17th century, our descriptions of it varied from an invisible, intangible, imponderable agent, or even threads of syrup which elongate and contract. And it was Benjamin Franklin who in 1752 set out to prove that there was a connection between lightning and these tiny shocks due to friction. In a famously dangerous experiment done alone with his son, he led a kite into a thunderstorm, and near the bottom, where the thread was wet, he tied an iron key. And after some time, he brought his knuckle up to the key and experienced a series of small shocks, identical to the ones created by contact with fur. This showed that indeed, lightning was simply the same thing as these household shocks, but on a massive scale. And at this time, people had begun to divide materials into two categories. One were objects which would allow or accept discharge, such as gold or copper, which we call electrical conductors. And interestingly, these materials are also generally good at conducting heat. And number two were objects which would not allow this discharge, such as rubber or electrical insulators. These materials also seem to insulate the transfer of heat. And we also began trying to measure this force that Thales had encountered. One way to do this was to suspend a piece of spongy plant, called a pith ball, from a thread. And when we rubbed an insulator against fur and brought it near the pith ball, it would pull on it, causing a deflection. If we added more objects, we noticed this deflection increased due to a greater pulling force. We also noticed that the shape of insulators made a difference. Large, thin insulators seemed to exhibit a much stronger force. And amazingly, it was found that conductors, such as copper wire, would transmit this pulling effect over a distance. This was demonstrated by running a long wire between the pith ball and the charged insulator. When the object was brought near the wire, it pulled through the wire and deflected the pith ball instantly. When we later touch the wire with our finger, a discharge occurs and the pulling stops and the ball is released. Immediately, people began speculating that this could be the future of optical telegraphs. And in 1774, French inventor Georges-Louis Lesage was one of the first on record to actually set up this idea. He sent messages through an array of 26 wires, each wire representing a letter of the alphabet. When a discharge occurred at one end, the pith ball would move at the other. The trouble with this telegraph was that it only extended between the two rooms of his house. The power of the deflection was small and difficult to work with, though at the time people were investigating techniques for generating larger charge differences in order to amplify the force involved. One improvement, popularized by Alessandro Volta 1 year later, was an easy way of generating discharges on demand. It was based on the idea that a charged insulator could induce or transfer a charge onto a nearby conducting plate. One needed to merely bring the metal plate close to the insulator, which would pull on the charge distribution in the metal plate, resulting in an imbalance or electrical tension in the metal plate. Then one could bring their finger to the plate and a discharge would occur. Then the plate is pulled away using an insulating handle, and an excess charge would remain trapped in the plate. The plate could then be discharged at will simply by touching it to a conductor, such as a finger. And amazingly, this process can be repeated many times without recharging the insulating plate. We could then generate many small discharges at will. And by now, Benjamin Franklin was focused on finding out how to trap or store up these discharges. At this time, he still assumed that electricity was some sort of invisible fluid, since he knew it could travel through water. So he assumed that water inside an insulator could hold electricity. What we now call the Leyden jar was a glass jar with water inside and a metal probe running out the top. Franklin also wrapped the outside in a conductive metal. When he brought a charged conductor towards the top probe, a discharge would occur and stay trapped in the jar. More importantly, was that the jar could be charged multiple times. Each spark would amplify the charge separation or electrical tension inside the jar. A good analogy is to think of the jar as a balloon, and each discharge as a short jolt of water. And after hundreds of iterations, the tension becomes massive. And to release the charge, he simply touched the outside conductor to the top probe. A large discharge occurred. Franklin improved the design over time, eventually realizing that the charge was not stored in the water, but the glass. The water was merely a conductive path from the probe to the jar. Today, we would call the Leyden jar a capacitor, or charge storing device. And when he chained many jars together, he found he could increase the capacity even more and release deadly bolts of electricity. And over the years, people focused on more effective ways of building up charge using friction machines, which could then be stored in capacitors and released as spectacular displays of man-made lightning. And over the next 50 years, people tried to design systems for sending sparks across greater distances using longer wires and more powerful discharges. However, sending electrostatic discharges as a communication method seemed clumsy, archaic, and was no improvement over the existing optical telegraphs of the day. They were widely ignored by government and industry. Though the tides were rising, an electric revolution was just around the corner.